You know that little ding your phone makes? It feels so simple, right? Well, behind that one sound is this massive, incredibly complex piece of engineering. Today, we're going to pull back the curtain and show you the actual architectural blueprint for the systems that power every single notification you get. Okay, let's get into it.
So, to really get a sense of the challenge here, you have to understand the scale we're talking about. This isn't just a few thousand messages. We're talking about a major application that has to reliably deliver 16 million notifications every single day. How in the world do you even start to design a system that can handle that kind of volume without completely falling over?
And look, that 16 million number, it's not all one thing. The system has to juggle three totally different channels. The lion's share, 10 million of them, are push notifications to your phone. Then you've got 5 million emails, and on top of that, another 1 million SMS text messages. Each one of these presents its own unique technical puzzle.
So here's our game plan. First, we're going to really understand the problem we're trying to solve. Then we'll do what any good engineer does, ask a bunch of clarifying questions. We'll start with a simple and, spoiler alert, super flawed design. Then we'll build a much, much smarter one. And finally, we'll see what it takes to make it truly bulletproof.
All right, let's start at square one. Before we can even think about building this thing, we need to know exactly what we're working with. Okay, first up, push notifications. Now, it's not like the app server just zaps a message straight to your phone. Nope. Instead, it sends a little package of data to a dedicated service run by, Apple or Google. Those services then use this unique device token. Think of it like a specific mailing address for your phone to forward the message on. And for SMS, it's pretty much the same deal. You call in the pros. I mean, can you imagine trying to build direct connections to every single mobile carrier on the planet? It'd be an absolute nightmare. So instead, developers just use a third-party service like Twilio. They handle all that crazy complexity, and the developer just makes a single, simple API call.
And yep, you guessed it, it's the same story for email. You might think, hey, I'll just spin up my own email server. How hard can it be? Well, it turns out making sure your emails don't instantly land in a spam folder is a full-time, ridiculously hard job. That's why companies pay for services like SendGrid, which not only specialize in high-volume delivery, but also give you all this crucial data on who's actually opening your emails.
All right, so we get the basic pieces now. We know what these things are, technically speaking. Now for what I think is the most critical step in any big engineering project, asking the right questions to figure out exactly what it is we need to build.
So what are the rules of the road here? First off, does it need to be real-time? Kinda. It's what we call soft real-time, which basically means if there's a slight delay when things get crazy busy, that's acceptable. We need to support the usual suspects, iOS, Android, and desktops. A notification can be triggered by something a user does or by a scheduled job on the server, and this one is huge. Can users opt out? Yes, absolutely. That is non-negotiable.
Okay, with our requirements locked in, let's sketch out our first attempt at a design. This is the most obvious, straightforward approach, and as we're about to see, it is a total trap.
The design is simple enough. All the different services that need to send a notification talk to one single centralized notification server. This one server does everything. It figures out who to send the message to, it builds the content, and it sends it off to the third-party gateways. Easy and clean, right?
Well, not so fast. The first critical flaw, and it's a big one, is that we've just created a massive single point of failure. If that one server crashes or just needs to be taken down for maintenance, the entire system is dead. Poof. No push notifications, no emails, no SMS. Nothing gets out. The second flaw is that it's incredibly hard to scale. What if we have a huge surge in email demand, but push notifications are just chugging along normally? With this monolithic design, we can't just scale up the email part. We have to scale up the entire server, which is wildly inefficient and gets very, very expensive. And finally, we create these awful performance bottlenecks. Some tasks, like building a complex HTML email, are slow. Other tasks, like sending a tiny push notification, are super fast. In this system, the slow tasks can clog up the whole pipeline, forcing the fast ones to wait in line. During peak hours, the whole thing grinds to a halt. So yeah, that first design is a total non-starter. Let's just tear it up and throw it out. It's time to build something much smarter. A system that's designed from day one for massive scale and for when things inevitably go wrong.
Now, the secret sauce here, the absolute game changer that solves all our previous problems, is this concept of message queues. Think of a queue as a buffer, a waiting area that completely separates the work of requesting a notification from the work of actually sending it. So check out this new flow. A service makes a call, the server grabs the data it needs, but then, and this is the magic part, it just adds a job to a message queue and moves on. It's instantly free to handle the next request. Sometime later, a totally separate worker server pulls that job from the queue and handles the slow, heavy work of sending the message. The bottleneck is gone.
Okay, we now have a solid, scalable design. But to make it truly production-ready, to make it something you'd bet your company on, we need to add several more layers of sophistication and safety. This is where we get into the stuff that keeps real-world engineers up at night. Reliability, to make sure we don't lose data. Notification settings, to respect user choice. Rate limiting, so we don't look like spammers. A retry mechanism for when things fail. And of course, security and monitoring to keep the whole system safe and healthy.
Let's tackle reliability first. To prevent data loss, the system saves every single notification in a database before it even goes into the queue. That way, if anything crashes, the request is safe. And to stop ourselves from sending duplicates, which is super annoying for users, we add a deduplication check. Every event gets a unique ID, and the system just asks, hey, have I processed this ID before?
And here's where the queue becomes so powerful. What happens if a worker tries to send an SMS, but that third-party service is temporarily down? In our old system, that notification would be lost forever. But here, the worker simply fails, and the job automatically goes back into the queue to be tried again a few moments later. It's a simple and beautiful way to handle temporary failures. And of course, none of this matters if we're just annoying our users. So the most crucial point is, before a worker even thinks about sending a notification, its very first step is always to check the user's settings. If they've opted out of that type of message, the job is immediately thrown away. User trust is everything.
So there you have it. We went on this journey from a deceptively simple idea, send a message, all the way to designing a distributed, decoupled, and resilient system that's capable of handling millions of daily messages. It's a perfect example of the hidden complexity that powers so much of our modern digital lives.
This whole massive architectural effort is hidden behind one of the simplest interactions you have on your phone. It really makes you wonder, doesn't it? Now that you've seen what it takes to send just one notification, what other seemingly simple features on your phone do you think are hiding a similar level of mind-bending complexity?